Hello. In this session, we are going to present the paper Fully Convolutional Graph Neural Networks for Parametric Virtual Try-On. My name is Raquel, and I prepared this work with my co-authors, Igor Santesteban, Elena Garcés, and Dan Casas. The digitalized reproduction of closed physical behavior is a common goal in computer graphics. Its applications range from visual productions to games or virtual try-on, and for some of these applications, it is key to have methods that work in real time. To this end, we introduce a novel data-driven model that is capable of predicting the deformation of a large family of garments as a function of the underlying body shape. A common approach to model clothes is to simulate its physical behavior by solving the equations of a discretized mechanical model. From mass-print triangle models to yarn-level simulation, physics-based models have proven to generate amazingly realistic results, and to generalize to almost any scenario. However, the computational cost of these kind of methods is usually extremely high, and despite the attempts done to improve their efficiency, they are usually too slow for a real-time environment. On the other hand, cloth reconstruction techniques aim to recover the accurate shape of real garments. These models can then be used to train data-driven methods, or as realistic 3D models. In the early attempts, markers and special acquisition sets were required, while deep learning techniques helped the latest to recover the cloth surface from a single image or to enrich the high-frequency wrinkles. However, they are mostly limited to a single topology. With the recent popularity of data-driven models in multiple areas, some approaches have been made to reproduce the deformations of clothes with this type of method. Recent works have shown how this technology can significantly improve the efficiency in virtual try-on applications, while maintaining quality, as well as offer some interesting design applications. However, existing techniques are limited to a fixed garment or topology input, and cannot cope with parametric garments with varying topology. In our work, we address this last limitation. To do so, we present a solution for virtual try-on applications based on fully convolutional graph neural networks that can handle garments of arbitrary topology. To prove its capabilities, we generate a parametric space of garments and drape them on parametric avatars. Our goal is to drape 3D cloth models with different topologies on arbitrary body shapes. To do so, we propose to decouple the problem in the three main sources of deformations and solve them in three different data-driven steps. In the first step, we train a regressor that returns a smooth draping of the parametric garment on a mean body shape. Then, after a topology optimization, our second step drapes a smooth version of the garment on the target body. Finally, the material-dependent wrinkles are added to the fixed cloth. We can actually train one regressor per material, creating different effects, depending on the desired material. Altogether, we got a full pipeline that allows the user to design garments using the design parameters and try them on arbitrary target body shapes. The parametric 3D drape corresponds to the pattern-dependent deformation, and it estimates the initial mesh configuration depending on three design parameters. The sleeves, the cleavage, and the length of the garment can be tuned using these parameters. The regressor drapes the garment on a mean body shape. It consists of a small fully connected network that returns the 3D positions of the vertices of the initial mesh, given the three design parameters. Notice that at this step, the topology of the mesh remains constant, and it is stretched to create the different garments. Then, we perform a topology optimization that generates a regular and homogeneous sized triangular mesh. This is required to accurately represent surface deformations in the input garment. See how this step avoids the formation of the generated triangles. Our graph neural networks take graphs as input, so let's see how we build our input graph for each sample topology. When we take a closer look, our garment is a 3D triangular mesh. It is made of a set of vertices and edges, which connect the vertices, forming triangles. For each vertex in the original mesh, we create a node, which is the concatenation of 3 different sets of values: the 3D position of the vertex, the rigging weights associated to the closest SMPL body vertex, and the SMPL shape parameters. The rigging weights serve as a descriptor of the position of the vertex within the garment. If two vertices are connected, then there's an edge between them, both in the mesh and in the graph representation. So, our first fully convolutional graph neural network takes as input the graph and returns the deformed, smoothly fitted garment. Remember that the graph contains information about the mean draped garment with the optimized topology and the target body shape. This step adds the mostly body-dependent deformation. The network is structured as a unit with fully convolutional layers, so it can take meshes of any size and connectivity. In the last step, a second and similarly structured fully convolutional graph neural network is trained to learn the high-frequency details that are mostly material-dependent. This step can be retrained specifically for different materials to reproduce its specific behavior. Training our networks just with reconstruction error cannot guarantee absence of collisions when it generalizes to new unseen topologies. Therefore, we propose a collisions loss, which increases when a mesh vertex gets into the body. For every vertex in the mesh, we find the closest body vertex and compute the collisions loss by comparing the vector between them and the normal of the body vertex, thus detecting and penalizing penetrations. The main advantage of this formulation is that, unlike the reconstruction loss, it doesn't require any ground truth data, so it can be trained with a self-supervised strategy, saving a lot of time in data generation. We fine-tune the already trained network and significantly reduce the number of collisions. To train our method, we generated our own synthetic dataset by simulating 2 different meshes of each of these 19 different garments on a range of 100 parametric body shapes. The 19 different garment styles are basically shirts with varying sleeves, shirts with varying cleavages, and shirts with varying lengths, from crop top to long dress. Notice that there are no combinations in the training set, like a long dress with long sleeves. In the next slides, we will show some results. Here, you can see how the network generalizes to new unseen topologies, creating realistic results. See that the method is still producing good-looking results in unseen garment types, like the long dress with long sleeves in the second row, or the crop top with low neckline in the bottom row. Here, we show how material-specific deformations can be achieved by retraining the last step of our network with simulations of different materials. We now compare our method with the state-of-the-art method by Santesteban et al., which is limited to a single garment of fixed topology. Both methods show equivalent results, while our method generalizes to a whole set of new garments and topologies. Finally, we created a demo that shows our method in an interactive environment. In our demo, you can see how the garment fits the shape on real time. The materials can be changed to see the different deformations. On the left, there's a design panel, where the 3 design parameters can be changed. Then, when the desired garment is selected, the topology optimization and sample computations are performed. After that, we can see how the garment fits the avatar depending on its shape. In summary, we created a parametric space for garment design that allowed us to create garments with new topologies and shapes. Then, with our fully convolutional approach, we got to drape garments of arbitrary topology on our parametric avatars. We present a full pipeline for parametric virtual try-on, which we believe is a step forward in the field, as it's the first one that generalizes to different topologies. Still, there is room for a lot of improvement. Our networks are trained in a static pose, and would need to be retrained in order to get a different pose. A straightforward improvement would be to treat the pose as an input to the network pipeline. Dynamics could then be added to create animations. With a bigger dataset, we could train the networks to work on a wider range of body shapes. Right now, we have to retrain the last network if we want to learn to drape a new material, but it would be interesting to use material as an input. We are aware that 3 parameters are not enough to represent the wide variety of clothes in the industry. Work could be done on making the design space richer. We thank the funding agencies for supporting our research, and thank you for attending. Have a nice day.